This is still section 6A, solving systems of equations by graphing. We're on page 54, as you can see. One thing that we didn't do last time was fill in this box right here. And we had talked about this particular example, example 4, not having any solutions because they didn't have a place where the two lines intersected. So let's go back and just fill this in. This system has no solutions. And we can write that with the null set symbol if we want, because the lines are parallel. And we know they're parallel because we ended up seeing that their slopes were the same, indicated by those arrows. Let's go down and do example 5. Again, we're going to need to graph both of these lines. In order to graph them, I put them in y equals mx plus b form because that's the fastest way for me to graph an equation. So if we take the first one, x plus y equals 3, move the x over, y is equal to minus x plus 3. We know that the slope is -1, that guy right there, and the b, the y-intercept, is +3. So that's that one. Let's look at the second one that they give us, which is 2x plus 2y equals 6. So we have 2y equals minus 2x plus 6. Divide each term by +2. And we get y is equal to minus x plus 3. So when you look at this, you go, well, okay, the slope is -1 and the y-intercept is +3, -1 right there. And you go, well, that's exactly the same. That means these are the same line. This is one line just smack dab on top of another line. So these guys, they intersect everywhere on the line because they're the same line. So every point that's on one line is also on the other line. So everywhere on the line is the answer to the intersection of those two lines. Okay, so actually, we said, where do these two lines intersect if we were to graph them? And I didn't finish the graph, so let's see. The y-intercept is 3, 1, 2, 3. The slope is negative, so it's going to be falling from left to right, and it's 1. So it's over 1, up 1, over 1, up 1, over 1, up 1, and then I'll come down and pick a few points in the first quadrant. So this is the line. And it actually happens to be two lines. They just happen to be on top of each other. So they are actually the same line. So what does that say about the solution to the problem? It says the real answer to this problem is that there are an infinite number of solutions, because there is no limit to the number of ordered pairs on this line. However, be careful. We cannot say all real numbers. Cannot, write this big, cannot say all real numbers, because all real numbers include every point on the coordinate plane. So there's an infinite amount of solutions, but they are only the points that are on this line. So be really careful. Don't say all real numbers. Say an infinite amount of solutions. So the next page, let's go on and do a little bit more on this video. A solution set for a system of two inequalities. Now we're talking about inequalities. So we've been dealing with equations, but now we go back to inequalities again. You might remember those. You might not want to remember those, but they are coming back to haunt us. So instead of being a line or a point on a line, it's going to be a region of the coordinate plane that satisfies both the first and the second inequality. So we must find the common region, the area that these lines have in common when you go work them individually. So we've got two lines here, they're written in slope-intercept form, so this is pretty easy to just go graph them. So I'm going to do that right off the bat here. The first one has a slope of -1 and the y-intercept is +2, so he's going to look like this. Remember, when we're dealing with inequalities, we have to decide whether we're going to fill the line in solid or is it going to be dotted. These are going to be dotted because it's less than, not less than or equal to, and greater than, not greater than or equal to. So when I connect these dots with a dotted line, that's what the equation of, and let me write this guy, this is y less than minus x plus 2. So now we have to figure out which part of the coordinate plane, up above or below, are we going to shade for this inequality. So again, if we look at the point 0, 0, if we plug in 0, we ask ourselves, what kind of statement does this make? Is 0 less than 2? Why, yes it is. So I am going to shade the part of the coordinate plane that has 0, 0 in it. Now I need to go look at the second line. We'll do him in green. Y greater than 2x minus 4. So minus 4, 1, 2, 3, 4, is the y-intercept. The slope is positive. It's 2. So up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. And again, he's a dotted line as well. So we're going to dot him. And we have to ask ourselves, which part of the graph do we need to shade for our green line here? So again, I'm going to pick 0, 0. So 0, I'm going to go check out my point 0, 0. 0, is that really greater than 2 times 0 minus 4? 0 greater than -4? No. 0, 0 is not a point in our solution. So wait, is this not working out right for me? Oh yeah, 0, I'm sorry. I pre-worked this and I'm not getting what I had. So yeah, of course, 0 is greater than -4. So we're going to shade the side where it's greater, where 0, 0 is a point. Now, to make this graph even a little bit messier, we need to shade the part of the graph that is in both of our solution sets. So if you're doing this with a pencil, you can lightly shade in the side for each individual line and then erase what is not part of your solution set. I can't easily do that. If I were to erase, I'd erase this green piece up here and I'd erase this blue part down here, and what that would leave is what I'm doing in red right now. Notice that the points on these lines are not included, so I'm not getting anywhere near those lines with my red pen, trying not to. But this part of the graph is the part that's in both of the solution sets for our two inequalities, so this is the guy that ends up being our answer. And it'll look a little bit better, like I said, if you do this with pencil lightly to begin with, then you can erase the sections that you're not going to use. Thanks for watching.